In this video, we will discuss real applications of normal distributions. A non-standard normal distribution is any normal distribution for which the mean is not 0 and/or the standard deviation is not 1. We can use a simple conversion formula to standardize any normal distribution so that x values can be transformed into z-scores. Z equals x minus mu over sigma. The figure below shows the conversion from a non-standard to a standard normal distribution. The area in any normal distribution, any normal distribution bounded by some score x is the same as the area bounded by the corresponding z-score in the standard normal distribution. Some calculators and software do not require the use of the formula given to convert z-scores, but if using table A2, we must first convert values to standard z-scores. The procedure for finding areas with a non-standard normal distribution. First, sketch a normal curve, label the mean and any specific x values, and then shade the region representing the desired probability. For each relevant value x that is a boundary for the shaded region, convert that value to the equivalent z-score. Use technology or table A2 to find the area of the shaded region. This area is the desired probability. Heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than 72 inches. The figure below incorporates the information in the problem description. The shaded region represents the men who are taller than 72 inches. We convert the height of 72 inches to the z-score of 1.21 by using our formula. Z equals x minus mu over sigma, which is 72 minus 68.6 over 2.8, which is 1.21 rounded to 2 decimal places. Use table A2 to find that the cumulative area to the left of z equals 1.21 is 0.8869. Remember, table A2 is designed so that all areas are cumulative areas from the left. Because the total area under the curve is 1, it follows that the shaded area in the figure on the previous slide is 1 minus 0.8869 equals 0.1131. The proportion of men taller than 72 inches is 0.1131, or about 11%. Note that the data on the previous slides shows an incorrect area of 0.1123, as does the interpretation given in the textbook. The US Air Force requires that pilots have heights between 64 inches and 77 inches. Heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. What percentage of women meet that height requirement? The figure below shows the shaded region representing heights of women between 64 and 77 inches. It incorporates the information given in the problem description. We find the shaded area using table A2 by first calculating the area to the left of 77 inches and then the area to the left of 64 inches, and then subtracting to find the area between them. For x equals 77 inches, z equals 77 minus 63.7 over 2.9, which is 4.59. So that yields an area of 0.9999. For x equals 64 inches, z equals 64 minus 63.7 over 2.9, which is 0.10. That yields an area of 0.5398. Subtracting, we find the area between 64 inches and 77 inches is 0.9999 minus 0.5398, which is 0.4601. This is slightly different from the area found when using technology, 0.4588, which is more accurate than using table A2. Either way, about 46% of women meet the height requirement to become Air Force pilots, and about 54% of women do not. Here are some helpful hints for cases in which the area or probability or percentage is known, and we must find the relative values. Graphs are extremely helpful in visualizing, understanding, and successfully working with normal probability distributions, so they should always be used. Don't confuse z-scores and areas. Remember, z-scores are distances along the horizontal scale, but areas are regions under the normal curve. Table A2 lists z-scores in the left columns and across the top row, but areas are found in the body of the table. Choose the correct right or left side of the graph. A value separating the top 10% from the others will be located on the right side of the graph, but a value separating the bottom 10% will be on the left side of the graph. A z-score must be negative whenever it is located in the left half of the normal distribution. Areas, or probabilities, are always between 0 and 1, and they are never negative. Procedure for finding values from known areas or probabilities. First, sketch a normal distribution curve. Write the given probability or percentage in the appropriate region of the graph and identify the x values being sought. If using technology, refer to the text center instructions at the end of the section in the book, page 249. If using table A2, as I have been doing all along, refer to the body of the table to find the area to the left of x, then identify the z-score corresponding to that area. If you know z and must convert to the equivalent x value, use the formula x equals mu plus z times sigma, which is a form of the formula given at the beginning of this presentation. If z is located to the left of the mean, make sure that it is a negative number. Refer to the sketch of the curve to make sure that the solution makes sense in the context of the graph and in the context of the problem. When designing equipment, one common criterion is to use a design that accommodates 95% of the population. In a previous example, we saw that only 46% of women satisfy the height requirements for US Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were to change to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. Assume that heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. The figure above shows the normal distribution with the height x that we want to identify. The shaded area represents the shortest 95% of women. Using table A2, search for an area of 0.95 in the body of the table. The area is a cumulative area from the left, and that is exactly the type of area listed in table A2. The area of 0.9500 is between the table A2 areas of 0.9495 and 0.9505. But there is an asterisk and footnote indicating that an area of 0.9500 corresponds to z equals 1.645.